All right, guys. So we are starting Unit 8 today, which is on gases. Now, if you notice on Canvas, it goes from Unit 6 to Unit 8. That is not a mistake. We're actually skipping our Unit 7 because we are trying to make things a little bit easier, a little less stressful towards the end of the year. And Unit 7 includes a lot of math. It's called stoichiometry. And so we decided to kind of skip that and just kind of go on to gases. And even in this gases unit, normally there are calculations with gases. We call them gas laws. And we calculate things like pressure and temperature and the volume of a gas and the number of moles of a gas and things like that. But again, we decided to kind of shorten the unit to kind of make it a little easier. So we're really only going to be talking about things like the properties of gases, the motions of gases, and we're going to talk about the gas laws, but we're just going to talk about them in terms of like the relationships between some of the variables like pressure, temperature, and volume. We're not going to be doing any calculations in this unit, okay? If you are interested in that stuff, like, stoichiometry has to do with doing math with chemical reactions and things like that. We do learn all that stuff in IB chemistry. So if you sign up for that, or if you've already signed up for that next year, then you will kind of learn that stuff in our class next year. That being said, I'm going to click on today's agenda. So if you notice, there's really only one thing for today. And that's because the notes have some questions and things built into them. And so as we're going to kind of go through it together briefly today, and then you guys on your own can kind of go back through it. You can take your notes, you can kind of write down anything you need to include. And then as you're going through on the pages, there are questions and things built in. And so just make sure that as you're going through that, like if there's any videos that you watch the videos, if there's any questions, you answer the questions and complete them, and that kind of stuff. Or if there's any kind of drag and drop things that you do that. Because then at the very end, it's going to have a button that says submit report, and you're going to submit that. And your notes and the questions that are built into them is actually what's going to count for your grade today. I did not make a separate assignment for today. So the beginning for today of gases is we're going to talk about what we call the kinetic molecular theory of gases. And we're going to talk about some of the basic properties of gases like temperature and pressure. And so when you go to your page, it's actually set up as an assignment, not a page. But I kind of put instructions up here that this H5P is going to serve as both your notes and your assignment grade for today. So make sure as you're going through that you complete any questions or activities and not just kind of read the information because you're going to have to submit at the end with your grade. So this is all about gases, gas particles. And so the kinetic molecular theory, if we kind of break down that term, kinetic has to do with motion. So in science, kinetic means motion. So kinetic energy is like energy of motion. And you learn about that, in junior high and then again in physics class usually. Molecular has to do with molecules. And so we're talking about the theory or the explanation for why particles move the way that they do. And so we usually talk about this in terms of gases because this theory describes how gases behave. So there's sort of 4 parts. Sometimes when you look at it online, there might be 5 statements. It kind of depends on where you reference to. But essentially, we say that gas particles are in constant motion. So all the particles they're always moving. They don't stop moving. Okay. They have no attractions or repulsions. So that means that they're moving past one another, and it's not like they're going to be attracted to each other and impact the movement. And so because of that, they always move in straight lines unless they collide with something. Now, when they have a collision, they're going to bounce off and just go the opposite direction. And so it's kind of like a billiard ball, which is like what you play pool with. So pool and billiards are the same thing. There's a lot of space between the particles compared to the size of the particles itself. So if you look here at these little particles, this particle is not that big, but if you look at the distance between that one and the nearest particle, the space is bigger than the size of that individual particle. So that's what number 3 is saying, is that the space or the distance between particles is a lot larger than the actual size of the particles themselves, okay? And then the last one says that the speed they move at increases with increasing temperature. And so basically what that means is if I increase the temperature of a sample of gas, the particles are going to move faster. And so what that tells us is that temperature and kinetic energy, which is energy of motion, they're directly related. So if I double the temperature, the kinetic energy doubles. If I divide the temperature by 3, the kinetic energy divides by 3. And that temperature has to be in a specific unit that we're going to talk about later. It can't just be normal like degrees Fahrenheit or degrees Celsius. So these postulates are true for most gases, okay? They're only 100% true in the case of what we call an ideal gas. So that's like an ideal gas is going to be ideal, meaning it's going to follow all four of these postulates. It's like it's going to be perfect. It's ideal, okay? But we don't live in the ideal world. We live in the real world. And so most gases are actually what we call real gases, okay? But for our class, we're going to assume that all our gases are ideal. And so they're all going to obey these postulates or these parts of the theory 100%. If you do higher up chemistry, like in college, you actually talk more about the difference between real gases and ideal gases, because you know how you do calculations for them are a little bit different. Because for real gases, you have to take into account some of the like attractions and repulsions and things like that. So then obviously you can see here there's a question. So again, make sure as you're going through that you do these questions that are embedded in here so that you have all of it completed when you submit at the end for your grade. So at the beginning of the year last semester, we talked about like solids, liquids, and gases. We learned about all the different phases of matter and that gases were included, okay? And so you can see kind of this image, all particles are always moving. It's just the type of motion that's different. So solids and liquids, because they're so close together, they do have attraction. And so they don't really pull away from each other like gases do. Gases, they're all moving randomly, okay? Solids are really close to each other, so they just kind of vibrate in place because they're so close that they're attracted to each other and they're in that kind of grid-like pattern usually. And liquids, they're a little bit further apart than the solids, but they're still close enough that they have some attraction, and so they don't really move apart from each other. Gases, though, they're so far apart that they don't have those attractions, and so that's why they move in those straight line motions until they, you know, they'll collide with like another particle or the wall of the container, and then they just kind of bounce off, which is what you see here, okay? So if you had like two gas particles and they were moving, so they're both moving in straight lines, and then they hit, and then they just bounce off like a billiard ball would, okay? There's no attraction, there's no repulsion, they just bounce off, and then they keep going in the other direction until, you know, it collides with another particle or it collides with maybe the wall of the container that it's in. And so because of the constant free movement, it says the volume of gas is mostly made of the space between the particles. So again, here in this image, there's two particles, they're relatively small, but then all around them is all this empty space. That's the empty volume, okay? In real life, they actually do experience attractions and repulsions that keep them from moving in completely straight lines. So ideal gases look like over here on the left, where they're straight lines until they hit something and then they bounce off, okay? Real gases, they're not really going in straight lines, okay? It's somewhat straight, but sometimes they're gonna have attractions and repulsions, so they are gonna kind of curve around and things like that. So temperature is one of the properties that we're going to see here when we're dealing with gases, because temperature is a measurement of the average kinetic energy, which is the energy of motion, as I mentioned earlier. So if you have higher temperature, that means that you're going to have faster average particle motion. So these three images right here, if you look at the little thermometers, this one looks like about maybe 5 or 6 degrees. This one's about 20 or 21 maybe. And this one's 40, 41. So obviously we can see the temperature is going up. And if you look at the little image below with the particles, you can see they're moving faster as you increase the temperature. So these are obviously, this is a solid because you can see they're all kind of connected, they're close together. And so what happens is as you increase the temperature, the solid particles, they start absorbing more energy and they start moving more and more because they have increased kinetic energy. And then eventually they're going to get to the point where the amount of kinetic energy that they have to move is going to be more than the attractive force holding them together. And that's when you have like melting, where it would turn from a solid to a liquid. And then the same concept applies to liquids turning into gases when they boil, okay? And so this is why temperatures explain how basic thermometers work. Because thermometer, usually you have a glass tube, it's sealed at both ends, okay? And it's usually partially filled with a liquid. What we have, most of our thermometers, they're going to be filled with alcohol. So the thermometers that have the red liquid, that's just alcohol that has some red food coloring or some kind of dye coloring in it. Mercury thermometers, mercury is a metal from the periodic table. So a mercury thermometer, it would not be red, it would be a silvery cup substance or a silvery color. Most thermometers anymore, they're not mercury because they stopped making mercury thermometers for like everyday use, because mercury is poisonous. So if a thermometer would break, you would have to clean it up because it's a metal. And so you can't absorb it with like a paper towel. So they have to be cleaned up a specific way. And it's poisonous, so it's dangerous. And so there are some labs, like chemistry and science labs, that will use the mercury thermometers because sometimes they're a little bit more precise than alcohol thermometers. But just for everyday life, your thermometers are always going to be the alcohol. And so what happens is when the mercury or the alcohol gets hotter, it expands in size, and that goes up. Okay, so anyways, yes, the mercury or the alcohol, as it gets hotter, it expands, meaning it increases in size, and so that causes it to rise up or go down as the temperature increases or decreases. So temperature, when you talk about gases and especially heat in chemistry, we actually use a different temperature scale. It's called the Kelvin scale. And so as temperatures increase, they decrease, particles move less and less until they stop. And so absolute zero is the temperature at which there is no particle motion, no molecular motion. That means that there's no kinetic energy, there's no heat, there's nothing. The particles have fully stopped moving, so there's none of that. And so that's why it's called absolute zero. And so it's actually measured on this scale called the Kelvin scale. So if you look at these three, they're comparing, this is the Fahrenheit scale. So you have degrees Fahrenheit, this is degrees Celsius, which is typically what science thermometers will measure in Celsius. So your thermometer, if you have like one at home that you use, like if you're sick or something like that, your thermometer probably measures in Fahrenheit, because in the United States, that is the common temperature scale that we use. That's what we hear on our weather reports and things like that. In other countries, though, that use the metric system, degrees Celsius is the common unit. So if you ever go to like countries like in Europe or Africa or South America, things like that, they will have like their weather reports are given in Celsius and not in Fahrenheit. Kelvin is sort of the science unit for temperature, especially for gases and for heat and thermochemistry. So these kind of show you how they're related. So on our scale here, we say water, normally it boils at 212 degrees Fahrenheit. Well, in Celsius, that's 100. In Kelvin, it's 373.15. Okay. Normally water, it freezes at 0 degrees Celsius or 32 degrees Fahrenheit, and that is 273.15 Kelvin. Okay, so absolute zero means it's 0 Kelvin. That is why the reason that they came up with this scale is because they started doing experiments and measuring, well, where will molecular motion stop? And they measured that it was negative 273.15 degrees Celsius. And they said, well, if temperature is a measure of molecular motion, and that's the temperature at which molecular motion stops, we should make that 0, because if the temperature is 0, that should mean it's all the motion has stopped. So that's why they developed this Kelvin scale, because if you notice, there's no negative numbers on it. It only goes down to 0 because that's where all particle motion stops. And so 0 Kelvin, which is called absolute zero, is equal to these temperatures in Celsius and Fahrenheit. So you can see it's a very, very low temperature, negative 459.7 degrees Fahrenheit, like super, super cold. Okay. So I kind of mentioned that you guys might already be familiar with Fahrenheit or Celsius, but when we talk about gases and thermochemistry, we'll typically be using Kelvin. So you need to know how to convert between Celsius and Kelvin. You don't really need to know how to convert between Fahrenheit and Kelvin, because Fahrenheit is not used in science because it's not the metric unit for temperature. So it's really easy, okay? Kelvin and Celsius, they have the same size temperature scale. It's just that it's a little lower. And so what happens is if you're given a temperature in Celsius, if you want to convert to Kelvin, you just add 273.15. If you're given a temperature in Kelvin and you need to convert it back to Celsius, you just subtract 273.15. So down here, there are a couple examples where you're going to convert from Celsius to Kelvin or Kelvin to Celsius, and you would just follow, using the information right here. Okay. I already kind of mentioned, but since 0 Kelvin's absolute zero, there's no such thing as a negative number for Kelvin. 0 is it. Okay. And so that's why we like that, because when we use this in actual calculations for gases, it makes the math a lot easier because there's no negative numbers. Okay. And so then you also have, again, there's some questions down here at the bottom, some multiple choice ones. There's 5 of them. So make sure you do that, as well as your temperature conversions here, so that you get the full credit for completing your assignment. All right, so pressure, temperature is one property of gas, pressure is another one. Pressure is defined, it's the total force of gas molecules colliding with the walls of the container. So pressure is caused by those particles hitting the walls or the sides of the container. So the more collisions you have over a period of time, the higher the pressure. And so anything that increases the collisions will cause the pressure to increase. Anything that decreases the collisions will cause the pressure to decrease. And so there are different things you can do to increase or decrease the amount of collisions. In this picture, if you can see that it's expanding right now, so the volume is getting larger, now it's contracting, meaning the volume is getting smaller. And so if you have a larger container, that means that you're going to have less collisions, because if you notice, as they expanded, they slowed down, they weren't hitting the walls, but now as it's contracting, they get faster and faster again. So as it's large now, you can see they're not colliding with the walls as much. Now as it gets smaller, they're colliding more and more. You can see them bouncing around more and more. So volume is related to pressure in that, as your volume increases, your pressure will decrease because there's less collisions because you have a larger space. So it's kind of like if you think about, if wherever you live, if you think about, the size of maybe like your room, if it's just you in there, but if you go into a closet, you're going to be more likely to hit the wall in a closet than you would in, like your entire room, something like that. So some of the units that we use to measure pressure, the official unit is called the Pascal, and it's abbreviated with a capital P lowercase a, but we have lots of other common units. So atmospheres, which are measured in ATM, pounds per square inch, which is abbreviated PSI, millimeters of mercury, which is abbreviated millimeters, MM, and then the symbol for mercury, HG. You can also have bars. You can also have what we call torrs, so abbreviated TORR. And then also sometimes instead of just pascals, they will have you use kilopascals. They'll put a K in front of here, and that just means that you've divided it by 1,000. So it's a kilopascal instead of a pascal. So just make sure that you're aware of all these and that all of these are different units that could be used to measure pressure. So again, here at the bottom, you have 4 questions. So make sure you're completing that. And then when you go to this last page, this is where it's going to give you your summary. So when you get here, so there's 12 interaction, or sorry, it's 12 scores. So there's 4 interactions. It's going to have, what pages you've interacted on, and then have you answered all the questions in their interactions. So make sure that, you have this all completed, and then here is where you'll hit submit report. Okay. If you're not sure what you haven't done, so for example, here, kinetic molecular, this is the check on the first page. There's no interactions on these pages, but then there's conversion practice with the temperature questions, and pressure questions. So it'll tell you if you're not sure what you missed, then it'll have this little summary, and you can go back to the page if you didn't finish one of the sections. Okay. And then you'll submit the report button here, and that is it. You will be done for the day.